Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello and welcome back to another episode of the A-Level Cookbook. Today we're going to be doing paper 1 from A-Level Chemistry in June 2021. This question is about enthalpy changes for calcium chloride and magnesium chloride. State the meaning of the term enthalpy change. So this is just a general term for enthalpy change. So this is the heat energy chain at constant pressure. You cannot just say energy change, you need to say heat energy change. Figure 1 shows an incomplete Born-Haber cycle for the formation of calcium chloride. Complete Figure 1 by writing the formulas, including state symbols, of the appropriate species of each of the three blank lines. So you've got 1, 2, 3 blank lines here. Let's have a look what's going on. So with Born-Haber cycles, you have your enthalpy of formation here, and it's a big old application of Hess's law. Because if you start from the elements in their standard states under standard conditions, and form CaCl2 here, then every single other step, starting at the elements in their standard states under standard conditions, going this way around will end up at the same point. So you are starting with their elements and ending with the product. So in this case, we're going to have solid calcium, that's it in its standard states, and then Cl2 gas. And it's a big application of Hess's law because you're starting from solid calcium and Cl2 gas and you're ending up at CaCl2, giving you this arrow here, the enthalpy of formation. If you were to take every single other route this way, like so, your atomizations, your ionization energies, your electron affinities, and so on, even though you took all of these separate routes, you've still ended with CaCl2 and you started with Ca solid and Cl2 gas. So the start and end are the same. A way I like to make sense of this is imagine this is your house here, and this is a store here, and they're like, I don't know, 1 mile apart. If you go from your house to the store, you've traveled 1 mile from your house. But if you decide you want to go all the way to Australia and back, so you set off from your house and you go all the way to Australia and then back to the store, you're still 1 mile apart from your house, even though you went all the way to Australia. It's the same thing here. The start and end point are the exact same, so the enthalpy change is going to be the same. So now let's actually label this. So we've already written our enthalpy of formation there. So let's have a look what's going on now. So the calcium's undergone the first ionization energy here, as you can see, because it's become, a Ca plus and E minus, and the chlorines have remained untouched. And then from this step to the next, we need to figure out what's going on. From this step to this step, we can see that calcium's gone from Ca plus and Ca2 plus plus 2E minus. So this step can't really be the second ionization energy, or else it would be here instead. But if we look at chlorine, you can see the chlorine has been atomized from Cl2 into 2Cl. So what's probably happened is the second ionization energies happened here, and then from this step to this step was the atomization of chlorine. On this step, you would write Ca2 plus, gas plus 2E minus, plus Cl2. And then from this step to this step, it's atomized, the chlorine. And then last but not least, we've got an arrow going down this way, and we've got an arrow going up this way as well. So the last part of the steps, to be honest. So what's happened is the electron affinities have happened to chlorine, giving you Ca2 plus gas plus 2Cl minus gas. It's taken on those two electrons, like so. Let's just put both of them in one step. Table 1 shows some enthalpy data. Use figure 1 and the data in table 1 to calculate a value for the enthalpy of lattice dissociation of calcium chloride. So let's have a look at what all the arrows are doing before we even start to do that. It's really important you know your enthalpy definitions. I know this seems like a lot to learn, but you have to know them. The reason being is because they help you identify what steps going on here. So the enthalpy of formation, for example, is where you're making 1 mole of a substance in its standard condition from their elements in their standard states, blah, 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 whatever, right? You're going from elements to the end product. So that has to be enthalpy formation. You can use those enthalpy definitions to work out what each step is. So we're going from calcium solid to calcium gas here. So this is atomization of calcium because you're atomizing the calcium. And we're going from calcium to Ca plus. So that has to be the first ionization energy of calcium. And then likewise, this has to be the second ionization energy of calcium. All right. And then we've atomized chlorine. However, the definition of enthalpy of atomization of an element is where you make 1 mole of gaseous atoms from an element in its standard state. There are 2 moles of gaseous atoms of Cl2. So there's actually 2 times that. And then from this step, from this step to this step, we've got electron affinity, but there's 2 chlorine, so there's going to be 2 times the electron affinity of chlorine. Now, we're a bit stuck because this arrow is going upwards. So we need to think what enthalpy changes we know. So we're going from a solid ionic compound to their gaseous ions. So that's the lattice enthalpy of dissociation. So now we have all the pieces together. Delta HF equals everything else added together. Presuming we're going this way. We're presuming we're going this way. However, this arrow is going up. So this kind of messes up the cycle because we want the arrow to go downwards. The enthalpy, the lattice enthalpy of dissociation is the exact opposite of lattice enthalpy of formation. So if I were to switch this arrow this way, it would be the exact opposite. So using that, the enthalpy of formation is minus 795. Then we've got the atomization of calcium. So that's going to be 193. And then we've got the first ionization energy of calcium, so that's plus 590. And we've got the second ionization energy, so that's plus 1150. And then we've got 2 times the atomization of chlorine, remember, because the definition is that you only make 1 mole of a gaseous, 1 mole of gaseous atoms from its element. So that's going to be 2 lots of 121. And we have 2 lots of electron affinity as well. But then we're stuck because this is the lattice enthalpy of dissociation that we're looking that makes this up. So instead of plus x, we'd write minus x because we're flipping the sign, right? Now I'm going to tidy everything up by just calculating the numbers and stuff. So minus 795 equals 93 plus 590 plus 1150 plus 2 lots of 121 plus 2 lots of minus 364. And then that gives you 1147 minus x. Subtract both sides by 1147. So minus 795 minus that gives you minus x equals minus 2242. So flip the sign, x equals plus 2242 kilojoules per mole. It's important that you include the plus or the minus. The reason being is because it's an enthalpy change. So if I tell you my weight's changed, you don't know if I've gained it or lost it. In the same way, we don't know if it's gained or lost enthalpy. So you need to say a plus. Magnesium chloride dissolves in water. Give an equation including state symbols to represent the process that occurs when the enthalpy of solution of magnesium chloride is measured. So it's asking you is to draw the equation for the dissolution of magnesium chloride. So the formula depends on the definition. So the enthalpy of solution is the enthalpy change when 1 mole of an ionic substance dissolves in enough solvent to form an infinitely dilute solution. So basically, it means we've got 1 mole of an ionic solid compound, so MgCl2 solid, dissociates into its ions in aqueous condition. So Mg2 plus aqueous plus 2Cl minus aqueous. Right. Table 2 shows some enthalpy data. So we've got the enthalpy changes, we've got the enthalpy of lattice dissociation, enthalpy of hydration, and enthalpy of hydration. Use your answer to question 1.4 in the data in table 2 to calculate the value of enthalpy of solution for magnesium chloride. So there's lots of different ways people talk about this. I've seen all kinds of God knows what formula and stuff. Just draw a Hess's law cycle. All right, so we've got MgCl2 goes to Mg2 plus aqueous plus Cl minus 2 lots of those aqueous. That is the enthalpy of solution. Now we need to look at what they've given us. They've given us the lattice dissociation of MgCl2. So if we dissociate this, then we would end up with Mg2 plus and 2Cl minus, which are gaseous ions. So Mg2 plus gas plus 2Cl minus gas. Now you need to think about this cycle and what's going on here. So if we're going from solid ionic compound to gaseous ions, that is the enthalpy of lattice dissociation. Now we're going from gaseous ions to aqueous ions. That's the enthalpy of hydration, which is why those definitions are crucial to know, because if you can do that, you can do the rest. So that means delta H solution equals delta H LE plus delta H hydration. All right, so always, always, always just draw out a cycle for all enthalpy changes, because then you can work out quite easily what's going on. That's why you need to know those definitions. So the enthalpy of solution would be the lattice dissociation enthalpy, so that's 2493. Add it plus the enthalpy of hydration of magnesium, but this obviously plus minus gives you that, so minus 1920, and then minus 2 lots of 364. Put that in your calculation, you should get minus 155 kilojoules per mole. The enthalpy of hydration of calcium 2 plus gas is minus 1650. Suggest why this value is less exothermic than that of magnesium. So always remember that bond breaking is endothermic and bond making is exothermic. We're making fewer bonds, there's less attraction going on. So need to explain why. The reason being is because the Ca2 plus ion is bigger. You cannot say Ca2 plus atom, that's wrong. It is an ion by definition because it's lost electrons. So it's bigger than Mg2 plus. But that's only one of them. I also need to explain the consequence of it. It's that there is a weaker attraction to the oxygen in water because that's how things dissolve. Of protons and neutrons in the atom's nucleus. Complete table 3 to show the number of neutrons and electrons. So we've got 46 titanium, 49 titanium 2 plus, and it says the number of protons is 22, 22. The number of neutrons is something, and the number of electrons is that. Right. So to work out the number of protons, you look at the periodic table, and the proton number will tell you what it is. Then you see the mass number here is 46, so the number of protons and neutrons has to add up to that. So 46 minus 22 gives you 24. The number of electrons is the same as the protons because this has no overall charge. So this is going to be 22. And then for that's 49. Yeah, 49 Ti2 plus. So the number of protons is still 22, or else it would be a different element. The number of neutrons is going to be 49 minus 22, which is 27. Now, in ordinary cases, again, the number of electrons is the same, but this has lost 2 electrons because it's 2 plus, so it's going to be 20. A sample of titanium contains 4 isotopes, titanium 46, 47, 48, and 49. In this sample, this sample has a relative atomic mass of 47.8. In this sample, the ratio of abundance of isotopes 46, 47, 40, and 49 is 2 to 2 to 1. Calculate the percentage abundance of 46 titanium in this sample. Right, so 46 to 47 to 49 is 2 to 2 to 1. Whoops, to 1. So I'm going to let the abundance of the 49 titanium 49 equal x. So this ratio is telling us that there's 2 times as much 46 as there is 49 and 2 times as much 47 as there is 49. So 49 has an abundance of x percent. 46 is going to be 2x percent. 47 is going to be 2x percent. Now we've worked out like an algebraic expression for all of those, but what about 48? We don't know what 48 is. Well, the abundances all have to add up to 100. So that means that 48 is going to be 100 minus all of these. So minus 1x, 2x, and 2x. So that means you're going to have 100 minus 5x. Now the percentage abundance formula is your relative atomic mass equals, and then every single abundance times the mass over 100. So we're gonna get 47.8 equals 49x plus 46 2x plus 47 2x plus 48 100 minus 5x, and that's all divided by. So if we times both sides by 100, we get 4780 equals, and I'm going to tidy this up now, 49x plus, what's 46 times 2? That is 92x plus 47 times 2, which is 94x, plus, and then 48 times 100 is 4,800, and then 48 times minus 5 is minus 240x. And I'm going to tidy up all the x's as well. So 4780 equals, so 49 plus 92 plus 94 minus 240 is minus 5x. So all your x's come up. Minus 5x plus 4,800. Subtract both sides by 4,800. So 4780 minus 4,800. So minus 20 equals minus 5x. So x equals 4. So now we know what x equals 4, but it's asking us for the abundance of 46 Ti. We said 46 Ti is 2 times x. So that means it's going to be 8%. Whenever you get questions like these, always list out each and every isotope, and then you can work out what it is. A lot of the time they ask you, like, they'll say, oh, there's, 2 times as much this as that, or whatever. Always call the lowest one X, and then, list out everything. So we know we've got 2 times X here, 2 times X here. And then there's always, like, one that's missing. They're expecting you to realize that that missing one is going to be 100 minus every single other one added up. So in this case, 100 minus 2x, 2x, and x, which gives you 5x. And you'll just do that and you'll be fine. This question is about elements in period 3 and their compounds. When a piece of sodium is added to 200 centimeters cubed in a large beaker, a vigorous reaction occurs and the temperature of the water increases by 25 degrees C. Give an equation including state symbols for the reaction of sodium with water and suggest why it's dangerous to react a similar piece of sodium with 10 centimeters cubed of water in a boiling tube. So the equation, you're going to react Na solid plus H2O liquid, and that gives us NaOH plus H2 gas. So we need to balance this now. So, well, you've got H here and H here, so 3H's here. So we need to make this sort of an even number on this side. So I'm going to make this 2 NaOH. So now we've got 2 H2s here and an H2 here. So that means we've got 4 H2s on this side. And if there are 2 H2Os there, we've got 2 Nas, so it's going to be 2 there. And that's your balanced equation. Now, it says, why is it dangerous? Well, the temperature is going to increase more, or the glass will explode or shatter, because they've done it in 200 centimeters cubed, and 25 degrees Celsius jump is pretty damn high. If they did that on a volume that's like 20 times less, that's probably going to be like pretty dangerous. So temperature will increase more. Give an equation for the reaction of phosphorus 5 oxide with water and suggest the pH for the solution formed. So we're reacting, so you should know that phosphorus 5 oxide is P4O10, not P2O5. That doesn't exist, I think. I don't know. It just, in AQA, like every single exam paper, it says do not allow equations from P2O5. So it's P4O10, P4O10 plus water. We need to think about what happens. A period 3 oxide of this forms phosphoric acid, which is H3PO4. H3PO4. So now we need to balance this. So we've got H3PO4 here. Well, we've got 4 phosphoruses, so I'm going to put 4 there. That gives you 12 12 H atoms. So that means there's going to be 6 here. Now it says give a pH. I'm going to say like 1. It's H3PO4. That's a bloody strong acid. So now it says explain in terms of crystal structure and bonding why silicon IV oxide has a higher melting point than phosphorus 5 oxide. Right. So whenever you're talking about anything like this, you need to describe the structure. So that means, what structure it is, and also what bonds. And then need to compare bond strengths. And then you need to describe the process of, overcoming the energy. So overcoming the bonds. So describe overcoming bonds in terms of how much energy is used. This should be 3 marks to you because if you follow that sort of process, you'll always get those marks. Okay, so silicon oxide is macromolecular. So SiO2 is macromolecular, which means that which means it's held together by strong covalent bonds. So those are the bonds that you're breaking, which require a lot of energy to overcome. That's what you need to say. You need to describe the bonds, so macromolecular. You need to describe that they are held by strong covalent bonds which require a lot of energy to overcome. Now, in macromolecular substances like diamond graphite, you are overcoming the covalent bonds. There are also, van der Waals forces and blah blah blah, but to be able to boil or melt a macromolecular substance, you need to break the covalent bonds. However, that does not apply to a simple molecule. All right. Because if I were to take P4O10 and break its covalent bonds, I'm breaking into P, 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 and O, 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 etc. That's not melting or boiling. You've essentially just broken this down into something completely different. If you're melting and boiling a simple covalent molecule, you are breaking the intermolecular forces, of which you need to describe which ones you are breaking. All right. So you can't just say intermolecular forces. That's not enough marks. So P4O10 is a simple molecule, and we're breaking van der Waals forces when heating, and these are weaker and require less energy to overcome. The amount of times I see people write something like, "Oh, you're breaking the covalent bonds," or "We're breaking intermolecular forces," you don't write that. You don't get the marks, and just don't do it. It drives me insane personally. Whenever you're doing these questions, if you've got a macromolecular substance, that's the only scenario you're breaking covalent bonds when you're melting and boiling. If you've got a simple molecule, you need to think, is there van der Waals forces? Is there permanent dipole-dipole interactions? And are there any hydrogen bonds? If you've got metallic bonds, the bonds you're breaking are between the metal ion and the delocalized electrons. And if it's ionic bonds, you're breaking them between oppositely charged ions. And then you need to know their relative strengths. So macromolecular and ionic and metallic are pretty damn bloody strong, so they all have high melting and boiling points. Simple molecules don't really have as high of a boiling or melting point. Another thing to appreciate is that van der Waals forces vary with the size of the electron cloud. So how big an atom is. A lot of people, they'll get a question where two things has van der Waals forces, and they'll absolutely fumble the bag and start panicking and be like, "Oh my god, I don't know what to write." If you think about it, iodine, I2, is a solid at room temperature, whereas water is a liquid. Water has hydrogen bonding and van der Waals, whereas I2 has van der Waals. Yet this is a solid instead of a liquid at room temperature. So what this is implying is that these van der Waals forces are stronger than both of these combined, which makes sense because iodine is bloody massive. It's a huge atom compared to, water. So there's more electrons, stronger van der Waals forces. So everyone kind of thinks of the four intermolecular forces as like, hydrogen strongest, then it's permanent dipole-dipole interactions, and then it's van der Waals. But van der Waals can outdo the other two if the atom's big enough. So an element in period 3 forms an oxide that is insoluble in water. This oxide reacts with sulfuric acid and aqueous potassium hydroxide. Give the formula for this oxide and give an equation for the reaction of this oxide with sulfuric acid. Okay, so in period 3, sodium and magnesium oxides are basics, so what they do is they neutralize acids. Silicon, phosphorus, and sulfur oxides are acidic, so they'll neutralize bases. The only weird one is aluminium, which is amphoteric. It can neutralize acids or bases. Now, that's a base. That's an acid. So our culprit is aluminium. So Al2O3. Now it says, write an equation for this reaction with sulfuric acid. So it's Al2O3 plus sulfuric acid goes to, and then you're obviously making a salt plus water. So Al2SO43, because that's got a charge of 3 plus, and that's got a charge of 2 minus, plus 3H2O, and then we need to balance that. So that's just going to give the formula of a hydroxide of an element that is used in medicine. So you could use MgOH2, which is used in neutralizing stomach acid. Identify the element in period 3 from sodium to chlorine that has the largest atomic radius. It's the one that's most to the left, so that's going to be sodium. The reason being is because as you move across the period, you're adding an electron to the same shell. Like you're not going up another shell if you're going in the same period. So that means that the attraction between the nucleus and the electrons is increased, so it actually draws those electrons in a little closer, giving you a smaller atomic radius. This question is about iron and its ions. Describe the role of iron as a heterogeneous catalyst in the Haber process. So we've got 3H2 plus N2 gives you 2NH3. Your answer should include the meaning of the term heterogeneous catalyst, how the iron acts as a heterogeneous catalyst, and the factors that affect the efficiency and lifetime of a catalyst. Okay, so first of all, let's talk about what heterogeneous catalyst means. So heterogeneous catalyst is in a different state of matter or phase to the reactants. And how do catalysts work? What they do is they increase the rate of reaction without being used up by providing an alternate reaction pathway. So how these catalysts work is, imagine you've got like your iron here, and you've got your hydrogen, and you've got your nitrogen, right? What they do is they adsorb to the surface, they stick, they don't go in. Absorb means to go in. Adsorb, zorb, means that it's sticking on the surface. What happens is, once they're stuck on the surface, the bonds are weakened between them, and you've got your nice little, they separate and stuff and whatever, and then you've got your NH3s forming. So it weakens the bonds and allows them to actually react, and then the products desorb. So hydrogen and nitrogen adsorb to ions surface, and the bonds and their bonds are weakened, and they react, and then the products desorb. So the products desorb, and that's it. There's that done. Now it says the factors that affect the efficiency and lifetime of the catalyst. So obviously we need to have, first of all, a big surface area. If I've got one big block of iron here, and let's say that's like, the container, then all I can do is have this on its surface like that. Whereas if I've got like tiny little balls of it, I can have them all over like this. So there's a massive surface area. Whereas that, I could fit loads more on a singular bit. So we need to use like small pellets or like a mesh. So small um, pellets or fine iron gives an increased surface area. As well as that, we need to discuss what can affect its lifetime. So what happens is you can have catalyst poisoning, which is where things bind to the catalyst and block its active sites. It's kind of like how enzymes work for those that do biology. So catalyst poisoning can happen, for example, with sulfur, which binds and blocks active sites for H2 and N2. Fe2 plus catalyzes the reaction between peroxide disulfate ions and iodide ions in aqueous solution. So you've got S2O8 2 minus and 2I minus gives you 2SO4 2 minus plus I2. Explain why this reaction is slow before the catalyst is added, and give two equations to show how Fe2 plus ions catalyze this reaction. So this is something that you guys need to specifically learn, which is, in the spec it says explain with equations how Fe2 plus ions catalyze the reaction between I minus and S2O8 2 minus. So let's get this bread. So first of all, why is the reaction slow before we add the catalyst? So the whole point of a catalyst is it reduces the activation energy. So one of the points we're going to mention in this question has to be that the activation energy is high. So activation energy is high. Now the next bit is to explain why. Because you can see we're reacting two negative ions and they repel. So like charges repel, opposites attract. So because two negative ions repel each other. Right. So the first reaction is that the so Fe2 plus ions are oxidized by the S2O8 2 minus. So if Fe2 plus is oxidized, then S2O8 2 minus is reduced. So this equation is Fe2 2Fe2 plus S2O8 2 minus goes to 2Fe3 plus 2SO4 2 minus. Now, you could learn this, or you could derive it by writing out the separate equations. So Fe2 plus going to Fe3 plus plus E minus, and then timesing that by 2, and then S2O8 2 minus going to 2SO4 minus, 2SO4 2 minus, and then balancing it by adding water and protons, etc. But you can see it's a 1 mark question. Well, I mean 1 mark for each of these, so it's probably best you just sort of learn those equations. And then what happens is this Fe3 plus now oxidizes the I minus to iodine. So if the if the I minus is oxidized, then the Fe3 plus is reduced. So that means the oxidation state of Fe3 plus decreases. So it goes back to Fe2 plus. So 2 Fe3 plus 2 I minus goes to 2 Fe2 plus I2. And it says, give a reason why Zn2 plus ions do not catalyze the reaction in this question. Well, obviously, we could say it has a full D shell, whatever, blah, 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 but like, that doesn't really explain why we've got stuff, why this actually happens. The reason this happens is because we've got variable oxidation states. You've got 2 plus and 3 plus. So there's more than one oxidation state. Zinc only has one oxidation state, so it couldn't do this. It could, it would just be Zn solid and it would be Zn2 plus. You can't have Zn3 plus, so this just wouldn't work. So zinc only has one, or sorry, zinc ions, I should say, sorry, only has one oxidation state. Or you could say Zn2 plus is the only ion it makes. Iron reacts with dilute hydrochloric acid to form iron 2 chloride and hydrogen, so Fe solid plus 2HCl gives you FeCl2 plus H2 gas. A 0.998 gram of pure iron sample, sorry, a 0.998 gram sample of pure iron is added to 30 centimeters cubed of 1 mole per decimeter cubed hydrochloric acid. One of these reagents is in excess and the other one limits the amount of hydrogen produced in the reaction. Calculate the maximum volume in meters cubed of hydrogen gas produced at 30 degrees Celsius and 100 kilopascals and give your answers to 3 significant figures. And in your answer, you should clearly identify the limiting reagent. So the way to work out the limiting reagent is to just work out the moles of each thing and see if they match. So the moles of the moles of iron would be its mass over its MR, so 0.998 divided by its MR, which is 55.8, and that gives you 0.0179 moles. Then we need to work out the moles of HCl. Now, in theory, the moles of HCl should just be 2 times this if we want to get a perfect reaction. So if we do the moles of HCl, that's going to be 30 times 10 to the minus 3, because you want to divide it or divide by 1,000 to get it into decimeters cubed, times 1, which is 0.03 moles. So the moles of HCl that we would expect is 0.0179 times 2, which is 0.0358. But we don't have that, we have less. Therefore, HCl is the limiting reagent because we don't have enough HCl to let this reaction go on to completion. If we had the full 0.0358, then this reaction would happen, but we've only got 0.03. So we've done that bit. We need to now we need to work out the moles of hydrogen gas. So a lot of people, what they might have done is they might have just used this number. That's not correct because all of the hydrogen needs to have come from this HCl. So therefore, the moles of H2 would be half of this. So 0.03 divided by 2, which is 0.0150 moles. If this was a perfect reaction where there was no limitation, then yes, you could do 2 times this. But in this case, you can't because we've not used, the appropriate amount of HCl. It's the limiting reagent. Therefore, the only amount, the highest amount we can make is whatever's possible from all of this because the H comes from here. So therefore, it has to, because they react in a 2-to-1 ratio, you've got half of this many moles, which we worked out as 0.03. So therefore, we have half of that, which is that. So there's the moles of that. Now, whenever we do these questions, always convert everything into the right units. This needs to be in standard, base units. So the temperature is going to be, so it's 30 degrees in Celsius. To convert it to Kelvin, you add 273. So this is going to be 303 Kelvin. And they've told you that the pressure is 100 kilopascals. So we need to convert that into the correct. So we need to change that into pascals, which would be 100. And they want us to work out the maximum volume in meters cubed, which is great because the formula actually requires it to be in meters cubed. So PV equals nRT. V equals nRT over P. So V equals the number of moles, which is 0.0150, times R, which is 8.31, times the temperature, which is 303 Kelvin, all divided by the pressure, which is 100. If we put that in, we should get 3.78 times 10 to the minus 4 meters cubed. And there you go. Figure 2 shows some reactions of iron ions in aqueous solutions. So we've got FeH2O6 2 plus, FeH2O6 3 plus, and we've got, if we add Na2CO3, we get precipitate A, we get Na2CO3, we get precipitate B. Now, unfortunately, I don't know any hacks for remembering transition metal colors. Like, there's no way around it, unfortunately, but otherwise, just memorizing them. Fe2 plus and the CO3 is 2 minus, so it's going to be FeCO3 and it is green. The formula B and states color. Give an ionic equation for the reaction of FeH2O6 3 plus with aqueous Na2CO3 to form B. So, okay, metal 2 plus ions, transition metal 2 plus ions react with sodium carbonate and they form insoluble metal carbonate. So they would form, the metal carbonates. In the example above, it's iron carbonate. Now, metal 3 plus ions don't form what you would think it would be. You would think it would be Fe2CO3 2, but it doesn't. So they act as stronger acids. So what they do is they form hydroxide precipitates instead. So what happens is that these carbonate ions react with H plus and remove them from the solution, and you get a salt plus water plus carbon dioxide. Whereas here you would get a salt plus water because these are stronger acids. You actually get a salt plus water plus carbon dioxide. So how I like to think of it is that 3 protons are taken away from this to react. So that means you're going to have Fe H2O3. Now the H pluses are gone, so all you're left with is OH minuses. So you're going to have 3 OHs, like so. Because Fe3 plus OH minus, you get they balance out basically. And you're left with the H pluses, which have gone and reacted with the sodium carbonate to form carbon dioxide gas. So in this case, its color is brown. So its ionic equation is going to be, okay, so what we've got is we've got FeH2O 6 3 plus reacting with a carbonate ion, so that's CO3 2 minus, and then that forms what we've made here, so FeH2O 3 OH3. Now, because 3 H pluses came from this and reacted with the carbonate ion, we're going to make 3 moles of water, so 3H2O. And now we need to balance the rest. And obviously we're going to have 3 CO2 because there's 3 of, 3 H2O, so 3 CO2s. So now we need to balance everything else out basically. So in that case, we're going to have 3 CO3 here. Okay, so then this balances out to 2 here and a 2 there. Explain why an aqueous solution containing FeH2O6 3 plus has a lower pH than an aqueous solution containing FeH2O2 plus. H2O6 2 plus, sorry, ions. Okay, so what this is talking about is it's comparing the acidity of 2 plus and 3 plus metal aqua ion solutions. So the way I like to think of it is that if you've got a 3 plus, you've got a pretty fat charge. You've got you've got the same, ion, like the same element, but it's got a 3 plus instead of a 2 plus. So the mass isn't massively different, but the charge has gone up by 1. So you've got a large charge to size ratio. This means that you've got much more polarizing power in the 3 plus than you have with the 2 plus. So this means that they can attract electrons from oxygen atoms of water molecules that are coordinately bonded to them and weak the OH bond. Therefore, it's more likely that an OH minus is released. If more OH minus is released, that means you have a more acidic solution, and that explains why. So Fe3 plus is smaller than Fe2 plus as it has a greater charge to size ratio. Therefore, Fe3 plus is more polarizing. So more OH bonds in water break and more H pluses release. Therefore, it's more acidic. Okay, so this question is about the equilibrium 2SO2 gas plus O2 gas gives you 2SO3 gas. State and explain the effect, if any, of a decrease in overall pressure on the equilibrium yield. So the equilibrium yield decreases. Why? Because if you're decreasing the pressure, then the equilibrium is going to shift to the side with more moles to try and counteract the change, which was to counteract the decrease in pressure. So whenever you're talking about equilibria shifting, you cannot just say to counteract the change. That's not enough marks. That's not enough detail. You need to say what the change was. You need to say how, so you can get the point across that it's changing whatever you did to it. So if an equilibrium, in this case, the equilibrium shifts to the side with more moles to counteract the decrease in pressure. If you say the change, it's way too vague. A pretty goofy example, I guess, is if I came up to you and I was on my like self-improvement arc of my life or something, and I was like, "Hey, yo, I've changed myself, bro." You'd be like, for the better, for the worse? What did you do? Did you change your fit? Did you change your hairstyle? Did you change your, what did you change? So in this case, it seems daft because they've told you in the question that they've decreased the pressure, but you need to just put that in there. Please just do it. It'll get you the marks. So the yield decreases. Whoops, I forgot to write the word decreases. Now why? It's because the equilibrium, I'm gonna write EQM for short, but you need to write equilibrium in your exam, shifts to the side with fewer moles. Why? To oppose the decrease in pressure. Okay, so a 0.460 mole of sample of SO2 is mixed with a 0.25 mole sample of O2 in a sealed container at constant temperature. When equilibrium is reached and a pressure of 215 kilopascals, the mixture contains this much SO3. Calculate the partial pressure in the equilibrium mixture. Right. So whenever you get a question where it's something like a certain amount of this many moles is mixed with this and then left to reach equilibrium. And then at equilibrium, you have this much. You need to work out the moles at the start and the end. So what I do is I write out the equation. So 2SO2 plus O2 goes to 2SO3. And then I write out all the equilibrium moles at the start and the end. You should do this with every single equilibrium you do, and you'll never ever get one wrong again. I can assure you, as long as you calculate everything correctly. So initial moles, let's write that out. So the initial moles of SO2 is 0.460, and it's been mixed with 0.250 moles of O2. Now, again, this is only at the start, so this equilibrium has like nothing, no SO2, SO3, because it's not reached that yet. Now, when we reach equilibrium, these react and whatever, and the reaction goes back and forth until eventually you hit 0.180 moles of 2SO3. So now we can use this to work out how much of each is left here. So in this case, the this has gone up by plus 0.180. So these will have had to decrease because they react with each other to make that. So because these are in a 1-to-1 ratio, this also decreases by 0.180. So that gives you 0.28. And then this decreases by half as much because if this decreases by 0.18 moles, because this is a 2-to-1 ratio here, this is going to have to decrease by half of that, which is 0.09. And that gives you 0.16. Right. So now we have our equilibrium moles. We now need to work out the partial pressure. So we need to work out the mole fraction. In order to work out the mole fraction, well, the mole fraction is equal to the mole of the gas interested, and you're interested in, over the total moles, which in this case would be the moles of the gas of interest, which is 0. So what is it? Oh, it's 0.280 over the total moles, which is 0.280 plus 0.16 plus 0.18. Yep, so which gives you 0.280 over 0.280 plus 0.16 plus 0.180, which gives you on this fraction. I'm just going to leave it in this form just so that we don't we don't lose decimal places and stuff. And then to work out the partial pressure, it equals mole fraction times the total pressure, which is your answer, 14 over 31 times the total, which is 215, and that gives you 97.1 kilopascals. That's how you do those questions. So, as a quick recap, whenever you have an equilibrium question where it says a sample of something is mixed and then it's left to reach equilibrium, the starting number has been given to you here. The equilibrium one is at the end. So, you need to write out the initial moles and equilibrium moles every single time. This goes with acids, this goes with Kc, Kp, K. Anything you do, it's this. And buffers as well. I see too many pupils trying to be all like, bloody Inspector Gadget, trying to be all clever and stuff, writing out some cryptic stuff, Only true ones will understand. Bro, the examiner you're gonna have, right? It's probably marked like 8 bajillion papers and is working on very little sleep. Husband slash wife's probably left them, taken all the money, taken all the good stuff, hogs the TV, and he's sleeping on the couch. Like he is not gonna go through and like sift through every single thing and be like, oh, this person kind of deserves a mark here. So you need to make sure your marking is clear, not only for you, for the examiner, but also for yourself. Because here you know what you've done, you can see what you've done, and you can use the results. The amount of times when I'm marking anyone's homework and I just see a mishmash of random numbers drives me insane, and also you end up making things mistakes. A different mixture of SO2 and O2 reaches equilibrium at a different temperature. Table 4 shows the partial pressures of these gases at this equilibrium. Give an expression for the equilibrium constant for this reaction and then calculate it for this reaction and give its units. So Kp is going to equal the partial pressure of your product squared all over the partial pressure of your reactants, which in this case is going to be squared because there's a 2 here, times the partial pressure of O2, like so. Do not write square brackets because this is partial pressures we're dealing with, not concentration. Now we need to actually work this out. So let's look at what the units are. So the units of all of these are in kilopascals. So you can just slap them in. So Kp equals partial pressure of SO3. So it's going to be 1.85 times 10 to the 2 squared all over the partial pressure of SO2, which is 1.67 times 10 squared, and partial pressure of O2, which is 1.02 times 10 squared. If we put all of that in, we should get 0.0120, which is, roughly 3, which is roughly 1.2 times 10 to the minus 2. Now we need to work out the units. So all you do is you just put the units in place of the squared bits. So in this case, we would have kilopascals squared over kilopascals squared times kilopascals, which would equal kilopascals squared over kilopascals cubed, which would equal kilopascals to the minus 1. Because if you're dividing powers, you subtract them. If you're timesing powers, you add them together. So it would be, so the Kp value would be 1.2 times 10 to the minus 2, and the units would be Kpa minus 1. What is the effect on the value of Kp if the pressure of this equilibrium mixture is increased at constant temperature? It stays the same. Now, why does it stay the same? In every single Ka, Kp, Kc, K anything, for the sake of A level, temperature is the only thing that changes the value. Pressure, concentration, and stuff like that does not change the value because all of the products and reactants will balance out just to give you the same value again. Temperature is the only one that changes it. Okay, so this question is about pH. Pure water dissociates slightly, so H2OL goes to H plus OH minus. The equilibrium constant Kc would be H plus OH minus H2O, and the ionic product of water is Kw. So explain why H2O is not shown in the Kw expression. Is that because the concentration of H2O is nearly constant? That's the whole reason why we do. So table 5 shows how Kw varies with temperature. So as the temperature increases, Kw also increases. Now, if we look at what Kw is explaining, it is explaining H2O dissociating into H plus and OH minus. So you're breaking bonds. So if you're breaking bonds, that is endothermic. All right. So the equilibrium, the forward reaction, that is, forward reaction is endothermic. Therefore, the equilibrium shifts to the right to oppose, not to just counteract the change, it's to oppose or counteract the temperature increase. Because if it's endothermic, what that means is it's going to absorb that extra heat energy to restore the temperature back to normal. So the reason we also know that this is going in the left direction this way is because Kw is increasing, and Kw is essentially, well, Kc here is, your products over your reactants, right? So as the temperature increases, the amount of product at equilibrium increases. So therefore, it also has to be endothermic anyway on that basis. Give the expression for pH and then calculate the pH of water at 50 degrees Celsius. Give your answers to two decimal places and explain why it's neutral at 50 degrees Celsius. So pH equals negative log to the base 10 H plus. Okay, so they've told us that Kw at 50 degrees Celsius is 5.48 times 10 to the minus 14. So if you have pure water, then in pure water, H plus and OH minus are nearly the same. So Kw roughly equals H plus squared. Therefore, H plus is going to equal the square root of Kw, which is going to be the square root of 5.48 times 10 to the minus 14. So we put that in our calculator. We get 5.48 times 10 to the minus 14. We get 2.34 times 10 to the minus 7. So 2.4 times 10 to the minus 7. We've got our H plus. Now all you do is you just put pH equals negative log to the base 10 of that answer that we just got, and it should give you the pH, which is 6.63. So it's a set, so 6.63. Then it says explain why water is neutral at 50 degrees Celsius. It's because each H2O molecule that dissociates gives one H plus and one OH minus. So they're balanced. It's like this. You have the equal amounts. That's why we made that squared assumption there. A pH meter is calibrated using a calibration graph. To create the calibration, the pH meter is used to measure the pH of separate solutions, each with a known accurate pH. So figure 3 shows the calibration graph. Use figure 3 to give the true pH value when the pH meter reading is 5.6. So it'll be there. Let's read across. So that's 5.5. 5.5, 5.55. A line isn't perfect. It's kind of like there. But I suggest why the pH probe is washed with distilled water between each of the calibration measurements. It's so that the previous solution doesn't contaminate the new one. So, obviously that would interfere with the pH probe measurements. Because either what would happen is that, you would have like residual stuff left over, which would either, neutralize or reduce increase the pH or reduce the pH. So we don't want to do that. So pH. The calibrated pH meter is used to monitor the pH during a titration of hydrochloric acid with sodium hydroxide. Explain why the volume of sodium hydroxide solution is added between each pH measurement is smaller as the endpoint of the titration is approached. It's so that you don't miss the endpoint to avoid missing the endpoint. When you do a titration, what you do is you kind of do a rough titer and you get some sort of value. Let's say it's like 25 centimeters cubed. The second time around you do it, you get close to 25, maybe like 22, 23, and you keep adding it really, really slow. So you just find that exact point that endpoint is. Otherwise, if you go straight to 25, you might have overshot it. The true value might have been like 24 point something. So that's why. Now, figure 4 shows the pH curve of a titration with hydrochloric acid and sodium hydroxide solution. So the hydrochloric acid was there to start with, and the sodium hydroxide was added because first of all it says on the axis, but also you can see the pH curve starts off really low and then gets really high. The student plans to do the titration again using one of the indicators to determine the endpoint. State why all 3 indicators are suitable for this titration. What makes an indicator suitable for titration is that their color change is within the pH range of the steep vertical part here, which in this case applies to all of them, 3.8 to 5.4, 6.8 to 8.4, and 9.3 to 10.5. The reason being is because this pH just suddenly shoots up. You want the color change to be where it suddenly shoots up, and that's when you know the endpoint is, because otherwise, if we had like an indicator here, that's kind of rubbish because the color change is much more gradual and slow, whereas here it's a sharp, quick, visualizable point. Whenever you're doing experiments and you're doing an endpoint where it's visual, you want to try and make it as clear as possible that that endpoint is reached. So that's why we like sudden color changes in things like titrations and other things as well. So, for example, the iodine clock reaction. Another example is if you're watching a precipitate form, you want to have like an X or something on a really big black X on like a piece of card or something, or like on the plate underneath the conical flask because then you can see it slowly fades away as the precipitate forms. So it's just trying to make that visual change more obvious. 36.25 centimeters cubed of 0.2 mol per decimeter cubed sodium hydroxide solution is added to 25 centimeters cubed of 0.150 mol per decimeter cubed hydrochloric acid. Calculate the pH of the final solution at 25 degrees Celsius, and they told you what Kw is. Now, in this question, whenever you're doing acids and bases reactions, you need to think about what's reacting with what. Is it a strong acid, strong base, or is it a weak acid, strong base? Because they have massively different steps in how you calculate. So this is a strong acid and a strong base. So that means they're just going to neutralize to form a salt and water. There's no KAHA stuff here. If it's a weak acid, then you have to use KAHA and all of that jazz. But here it's a strong acid. So just to get my head around things, what I'm going to do is I'm just going to write a very quick reaction for this. So we've got NaOH plus HCl. It's a neutralization reaction. So you're going to have NaCl plus H2O. All right, this is helpful. Always write the equation out. It just gets your bearings in place as well. So the moles of NaOH is going to equal its concentration times volume. So 36.25 divided by 1,000 or times 10 to the minus 3 times 0.2 gives you 7.25 times 10 to the minus 3 moles. And then the moles of HCl equals 25 times 10 to the minus 3 times 0.150, which is going to give you 3.75 times 10 to the minus 3. So you can see that there's more NaOH than there is HCl. So the moles of excess NaOH is going to equal 7.25 times 10 to the minus 3 minus 3.75 times 10 to the minus 3, which is 3.5 times 10 to the minus 3 moles. Now, because this is a strong base, NaOH dissociates entirely, nearly entirely, into Na plus and OH minus. The OH minus is what we're interested in here. So therefore, your moles of OH minus equals 3.5 times 10 to the minus 3. Now, whenever we're working with bases, Kw is what you're going to end up using because it's the only thing that relates, H plus and OH minus together. Ka doesn't do it. All the other ones don't, so it's going to be Kw. So Kw, as a reminder, is the concentration of H plus times the concentration of OH minus. Now we have the moles of OH minus, but we don't have the concentration. We want to work out the concentration of OH minus. So the concentration equals moles over volume, which is going to be 3.5 times 10 to the minus 3 moles over the new volume because you're mixing two solutions together. So the new volume is going to equal 36.25 plus 25, which is 61.25. So you're going to divide it by that, but you obviously want to convert that into decimeters cubed. So you divide that by 1,000 or times 10 to the minus 3, and the concentration should be 5.71 times 10 to the minus 2. That now you slap it into this equation. They told you Kw, so is 1.00 times 10 to the minus 14, and that equals H plus, which is the concentration of H plus, sorry, and then 5.7 times 10 to the minus 2. So the concentration of H plus equals 1 times 10 to the minus 14 divided by 5.7 times 10 to the minus 2, which is 1.75 times 10 to the minus 13. Now you've got the H plus, you slap into the pH formula, so pH equals negative log to the base 10 of your answer, which is 12.76 to do 2 decimal places. Whenever you're doing an acids and bases question, and you've got a base that's left over, or they want to find the pH of a base, you're going to end up using Kw. If it's a weak acid, you're going to have to use Ka. If it's a strong acid, strong base, then you don't need to use Ka. You just do what we did here. So always write out the reaction over in the top and just think to yourself, is this a strong or a weak acid? Because that changes your steps beyond that point massively. Okay, so this question's about thermodynamics. Consider the reaction below. So you got 2Al2O3 solid plus 3 carbon solid gives you 4Al solid plus 3 CO2 gas. Table 7 shows some thermodynamic data. So you've got the enthalpy of formation of Al2O3, ALS, CS, and CO2 gas, and then we've got the entropies of each thing. So it says, explain why the standard entropy value for carbon dioxide is greater than that of carbon. It's because CO2 gas is more disordered than solid carbon. So entropy and is the measurement of disorder. It's how disorganized something is, how many ways you can spread energy in a system. So solids have very little entropy because the particles are stuck in place, vibrating in situ. Whereas a gas, it's whizzing around freely, so it has a huge amount of disorder. State the temperature at which the standard entropy of aluminium is 0 joules per Kelvin per mole. You can see there, it gives you a hint. Entropy is measured in joules per Kelvin per mole. So if you have 0 moles of it, you're going to have 0 entropy. If you have 0 Kelvin, you're going to have 0 entropy. So it's 0. And that makes sense because if you're in absolute 0, 0 Kelvin, nothing's moving. It's absolutely still. So there's going to be no disorder. Okay, so use the equation and the data in table 7 to calculate the minimum temperature in Kelvin at which this reaction becomes feasible. So this is involving Gibbs free energy change. So delta G equals delta H minus T delta S. They've not given us delta H and delta S, so we need to work that ourselves. So I'm going to just sketch this equation here just for our sake. So 2Al2O3 plus C 3C gives you 4Al plus 3CO2. In order to work delta H out, we need to use this enthalpy here. So we're going to draw a Hess's law cycle. Now, whenever you do enthalpy changes like this, and you're trying to find something that's like, indirectly related, always draw a Hess's law cycle. It just goes unbelievably crazy. So in this case, these are enthalpies of formation. So the definition of enthalpy of formation is where you make 1 mole of a substance from its elements in their standard states under standard conditions, right? So down here, we're going to effectively have the elements. Now, because it's enthalpy of formation, you're going from elements to the end products, the substances that have been formed. Now, it's told you that the enthalpy of formation of Al2O3 is minus 1669. So that means you're going to have 2 lots of minus 1669 because the definition says you need to have 1 mole of a substance from their created from its constituent elements, and the standard says blah blah blah, right? It's 1 mole. So this, because there's 2 moles here, we're going to need 2 lots of that enthalpy. So another thing as well I just want to mention is that it is essential that you know those enthalpy definitions, because if you don't, then you're screwed in pretty much anything to do with thermodynamics, Hess's law, Born-Haber cycles. You're just doomed. Anything enthalpy related, it's game over. Now, enthalpies of elements do not have, the enthalpy of formation of elements is always just 0. And then CO2, they've told us, is 394, minus 394. So there's going to be 3 lots of minus 394. So Hess's law says that this route is the exact same as going around this way, like so. And that makes sense because you've got the same start and finish point. If you live here and this is the store, this is 1 mile away. It doesn't matter if you go all the way to Australia and back and travel the entire planet, you're still this distance away from your home. So it's the same thing here. So delta H of this whole reaction equals this cycle going around this way. So we're going against this arrow, we're going against this arrow, we're following this arrow, and we're following this arrow. So when you're going against an arrow, you need to flip the sign. So we're going against that arrow, so it's going to be 2 and then 1669 instead of minus. The 0, 0 doesn't matter, plus 3 lots of minus 394. So that means delta H equals plus 2156 kilojoules mole. So you've got delta H. Now we can work out delta S. Delta S is just it's just S products minus S reactants. So the N minus the start. So S products is going to equal 4Al, so that's 4 times 28, plus 3 lots of CO2, so that's going to be 3214, which is 428 plus 3214, that's 754, and then S reactants is going to be 2 lots of Al, so there's 2 lots of 51 plus 3C, so it's going to be 3 lots of 6, which is 120. Therefore, delta S equals the products minus the reactants, so 754 minus 120. 754 minus 120 gives us plus 634, and this is in joules per Kelvin mole. Now, it's important to appreciate, and they also give it in the table as well, is that the enthalpy change is in kilojoules per mole, whereas this is in joules per Kelvin per mole. So when we're getting to the calculations, we're going to have to times the enthalpy by 1,000 to get that into joules per mole. So now, when a reaction becomes feasible, delta G equals 0, okay? So delta G now equals 0. So 0 equals delta H minus T delta S, right? So we can rearrange this now, and you get T delta S equals delta H, and then T equals delta H over delta S, which in this case is going to be delta H, which we worked out to be 2156, but that's in kilojoules per mole. We need to convert that to joules per mole, so it's going to be times 1,000 divided by the entropy change, which we worked out to be 634 joules per Kelvin per mole. If we do that, we should get, let's see, 2156 times 1,000, 634, 3,400 degrees Kelvin. Now, some people that I know have tried learning this equation and using it all the time. Do not do that. This equation only works if delta G equals 0, because that's where you've derived it from. If a question has a delta G value that isn't 0, then this equation does not work. So do not memorize that. And if you're going to memorize it, only understand that that works if delta G is 0. Otherwise, it does not work. So I just want to really drill that into people. Okay, so this question is about electrode potentials and electrochemical cells. State the meaning of the term electrochemical series. So all it is, it's electrode potentials in numerical order. So table 8 shows some electrode potentials, blah, blah, blah. State two conditions needed for this following half cell to have an EMF of 0 volts. So we got H plus E minus goes to half H2. So what this is trying to get at is that this is your standard electrode potential. So when you've got a standard electrode potential, you're comparing whatever you're testing against the hydrogen electrode potential. So for this to have we work on the assumption that this EMF is 0. And the only time that's ever valid is when you have it in standard conditions. So the standard conditions are 298 Kelvin and 298 Kelvin or 25 degrees Celsius is what I meant to say. And you've also got to have the H plus concentration as 1 mole per decimeter cube, or you can also include that the pressure is 100 kilopascals. So if you change any of those, that would shift this sort of reaction equilibrium to the left or to the right, and therefore it would change this. So scientists across the planet were like, all right, lads, this is standard conditions, and we're going to work on the assumption that this is going to be 0, because every single other one of these is compared to that hydrogen. Okay, so identify the weakest reducing agent in table A. So reducing agent reduces something else. If something else gets reduced, something else has to be oxidized. So reducing agent reduces something else and itself becomes oxidized. So the more negative you are, the better you are at becoming oxidized yourself. So therefore, this is the weakest reducing agent. So it has to be really bad at reducing something else. So it has to be really bad at getting oxidized itself. So that means it has to be the most positive thing here, which in this case is going to be CO H2O 6 2 plus. Use half equations from table 8 to deduce an equation for the reaction of this to this in aqueous solution by iron. So it's not saying iron ions or anything, it is solid iron. So we've got Fe solid. So this is the equation that's getting reduced. So it's gonna follow the same reaction that way around, sorry. So it's gonna be VO 2 plus 2H plus E minus goes to VO 2 plus H2O. Now, because we're going from solid iron all the way up to this oxidation state, solid iron becomes Fe3 plus 3E minus. Because if we were using this, that's not with solid iron, because you would start with FeH2O6 2 plus, but they've asked you to do it with iron to start with. So what happens is the iron is oxidized into 2 plus, it's 2 plus form, and then it's 3 plus form. So in essence, Fe solid becomes Fe3 plus 3E minus. Now we need to balance those equations. So you balance the number of electrons, and then so it's just a case of timesing it by 3 and combining the two of them. So that's why you get V3VO2 plus 6H plus 1 lot of that Fe. And this is aqueous, this is solid. Goes to, and the electrons cancel out, remember? So that's going to be 3 times that. So 3VO2 plus 3H2O plus Fe. This question was a bit weird, and I looked at the examiner report, and many people got it wrong for this reason. Very odd. But again, 2 marks. Not worth the stress. Use data from table 8 to explain why COH2S6 3 plus aqueous will undergo a redox reaction with FeH2O6 2 plus, and give an equation for this reaction. Let's pick out what we're looking at here. So CO, so it's this one here, and this is undergoing a redox reaction, so it's this. and FeH2O6 2 plus, which is this. So why does it happen? Well, the EMF of CO3 plus CO2 plus is greater than Fe3 plus Fe2 plus. So one of them is able to get oxidized and one of them is able to get reduced. So in this case, since this is a higher one, okay, so since this is lower, this one's going to be oxidized and this one's going to be reduced. So then you can just balance out their equations and slap them together. Because they have the same number of electrons, you can just add them together. So this one is reduced, so it's going this way because it's adding the electron on. So it's going to be CO H2O 6 3 plus the stuff in iron, but the other way around. So it's going to be plus Fe H2O 6 2 plus. You don't need to add the electrons because they cancel out. Goes to, and then CO H2O 6 3 plus Fe H2O 6 3 plus, like so. So suggest why the two cobalt complex ions in table 8 have different electrode potentials. It's because they've got different ligands. I mean, you can see this one's got H2 and that one's got an H3, so they're probably going to behave differently. So different ligands. They have the same oxidation state, 3 plus and 3 plus. It's all going to be that. So it's probably the fact that they have different ligands. You can conclude that because that's essentially the only thing that's different between the two. This question is about the development of lithium cells. The value of E for lithium suggests that a lithium cell could have a large EMF. So we've got minus 3.04, and then we've got like, this is the lithium, this is water, and this is iodine. So use data in table 9 to explain why an aqueous electrolyte is not used for a lithium cell. Okay, so compare the two of them. So this one's more negative, so that one's going to be oxidized and that one's going to be reduced. So what would happen is the water would oxidize the solid lithium to Li+. So water would oxidize Li solid to Li+, which we kind of don't want to do. So in essence, they react. Let's see. In the 1970s, lithium iodine cells became a common power source for heart pacemakers. Lithium iodide is the final product of the cell reaction. Use the data in table 9 to calculate the cell EMF of a standard lithium iodine cell. So we've got iodine, we've got lithium. So this one's being reduced and this one's being oxidized because this one's more negative. So EMF equals reduced minus oxidized, which is 0.54 minus 3.04, which equals 3.58 volts. An EMF for a commercial lithium iodine cell is 2.8 volts. Suggest why this value is different from the value calculated in question 9.2. So again, we talked about it before, the hydrogen potential, the standard hydrogen electrodes, right? Is these are all recorded in standard conditions. You're not going to perfectly use it in a place where, you've got 25 degrees Celsius temperature and you've got 100 kilopascals pressure. So it's non-standard conditions. That's why it's going to affect that. In some lithium cells, lithium perchlorate is used as the electrolyte to reduce the oxidation state of chlorine in lithium perchlorate. So if you split it up into its little bits, so LiClO4. So the oxidation state of O4, oxygen is always -2, so that's going to be -8 overall. Oxidation state of lithium as a salt is going to be +1. So +1 plus X plus -8 equals 0. Sorry, equals 0. So you're going to have X plus 1 minus 8 equals 0. So X has to equal 7. So it's +7, sorry, in this case. In other lithium cells, lithium cobalt oxide electrodes and lithium electrodes are used. Give an equation for the reaction that occurs at the positive lithium cobalt oxide electrode. Right, now this is a specific example AQA requires you to know. So the positive one is going to be, it's going to be Li plus solid plus COO2 aqueous plus E minus goes to Li plus and then COO2 minus solid. Give an equation for the reaction that occurs at the negative lithium electrodes. It's going to be LiS goes to Li plus aqueous plus E minus. And there you go. Thank you very much. I hope this tutorial's helped. The usual, please like and subscribe, share with all your friends, and good luck for those that are taking their exams at this point in time.